Hello everyone. I have a new video for you. Go over the beginnings of chapter 13. You can go through this quickly here. I put this in a notability, so the view should look similar to this if you're doing the same yet. Make some annotations where it's necessary. But this is drawing back to kinetic theory. And if you remember, kinetic theory is about the movement of molecules. And if you recall, when we went over like states of matter, we said that a solid, there's an adhesion amongst the molecules, and the kinetic energy isn't strong enough to break that adhesion, so they're locked into place. With a liquid, there's enough kinetic energy they can move freely, but they're still pretty close together. And with a gas, there's almost no attraction amongst the molecules. So I just want to remind you of that before we go further into this as a model of gases. Excuse me. I'm not one with notability too much, so you'll have to forgive me. Okay, so the word kinetic refers to motion. Again, has to do with the movement of molecules in this case. So kinetic theory, all matter consists of tiny particles that are constant motion. And if you recall, even in a solid, they're still moving. They're just locked in a position. If you remember, we talked about them vibrating in place. This is way back, beginning of the school year, back in September, October. I don't know if any of you remember back that far. It seems like forever now. But anyhow, particles in a gas are considered to be small, hard spheres. That's the molecules. But if you recall, we talked about how gases, the molecules are so teeny tiny that in the bigger volume of the gas, they make up a very tiny amount of the actual volume. Most of the volume is going to be open space. Okay, now you can compress gases and so forth. We'll talk about that in the future. But essentially, most of what is there in a gas is open space. A great example of this is, I think I told you the example of when the aerosol can was in the trash burner and it about made me have a heart attack. But kinetic theory as it applies to gases includes the following fundamental assumptions. Gases will fill their containers. They do not have a specific space, and they will spread out into without limit. Essentially, if you have a giant space and you fill it with a gas, if the gas is a small amount, it means the particles or molecules will be really, really far apart. Okay, so I don't know if you guys have ever seen like NASA, but I'll show you this quick here. NASA uses something like this. It's a giant vacuum chamber, and they would test like their the space shuttle and stuff in there. Okay, you can kind of get an idea the magnitude of the stuff NASA gets to play with here. But you see, here's the outside of one. Here's the inside of one. Again, it's big enough they can stand up a space shuttle in some of these. There's part of a rocket in one, and the reason they do that is so they can test the effects of space on their space vehicles, because once you get into our outer atmosphere, the gases are so thin, it's not quite a vacuum, but it's getting pretty close. But if you were going to send like a probe out to, say, Venus or something, or the Neptune, I can't remember the I think it's Viking is the one that's traveling way out the edge of our solar system now. You can't test that stuff in space. You got to test it here first. And that's where they do it, in these vacuum chambers. Again, NASA's got some really big ones, not like anything we can have access to. But anyhow, kinetic theory as applies to gases includes the following fundamental assumptions about gases. If you look, the molecules, they're going to hit each other, okay? They will strike, and they will strike the edges of the container, okay? Now, what happens with this rapid constant motion if you increase temperature? Well, then you increase kinetic theory or kinetic energy. Kinetic energy means more movement. More movement means more strikes on a side. So that's why when you have a closed container and you heat it, the gas inside gets hot and the pressure goes up. Okay, you didn't put more gas in it to make the pressure go up. Instead, it's just a function of the characteristic of gases in kinetic theory. Okay. Basically, the particles will travel in straight line paths until they collide with another particle or the edges of the container. During an elastic collision, kinetic energy is transferred without loss from one particle to another. Essentially, think of it as like two pool balls hitting. Okay, if you were to look at them and they were to hit, well, probably a better example would be like two tennis balls hitting in the air. Okay, they'll mushroom and react to each other, right? They're traveling towards each other, and they'll look something like a ball and a ball, right? But when they smash into each other, they'll probably look something more like this. Oh, I didn't want to do that. That's terrible. Let me try one more time. That's real bad too. But you get the idea. You're going to get this smashing effect, okay? Yeah, that's terrible. But essentially what will happen is, and you can Google this or YouTube it, when you get two objects and they smash together, they're going to deform, and then they'll rebound off each other and repel backwards. Okay? Same thing would happen with the molecules in a gas. And here you see the explanation for that. So anyhow, gas pressure. Kinetic theory explains gas pressure. How? Well, it results from the force exerted by the gas per unit surface area of an object. Think about a finite amount of gas, okay? Let's just say you had a liter of gas in a liter-sized container, okay? It's going to have a specific pressure, okay? But if you alter some of the other factors, like temperature, or you can alter the size of the container, you can alter the pressure, okay? A specific gas or a specific volume of a gas can have a different volume at a different temperature, in other words. Or it can occupy a different volume, but pressure is always going to be something that fluctuates because of that. It's the result of billions of rapidly moving particles in a gas colliding with other objects in the gas molecules, and the size of the container itself. If there are no particles, there are no collisions, and that's where you have no pressure, and that's what you would have inside of a vacuum, right? Or space. Okay? Air exerts pressure on Earth because gravity holds particles of air within Earth's atmosphere. If you jump out of a plane and you're going skydiving, the Earth would pull you towards it. Well, air molecules are not, they're not an exception to gravity. Earth's atmosphere is thicker near the Earth's surface. Now, as you go up in the atmosphere, like if you were climbing a mountain, it would literally get thinner. And I'm sure you've all, heard about how things go when people are climbing like Mount Everest. The air gets thinner. They can only climb for a few, sometimes 15, 20 minutes, and then they have to take a break, sometimes for hours, to build up their oxygen again. Barometer is a device used to measure that. It's measured in millimeters of mercury. That's usually, it was measured, a lot of times it was measured in millimeters of mercury when this was the best piece of equipment they could find. Now they have pressure gauges that are much more scientific, okay, and they don't have poisonous mercury in them. But anyhow, when weather forecasters state that low pressure systems moving into your region, it means that a storm's coming, typically, because low pressure, what happens with low pressure is it's usually cooler air, and it drives a wedge underneath the warm air. So here you have a high pressure system, okay, high pressure in place, and then you have a low, and it's usually they usually draw it like this. Okay, you've probably seen it on a weather map, but actually what happens is the low is colder, low pressure air, and it's heavier. So when it meets the warm air, it creates a boundary, okay? Here you have the warm air on this side, and the cold, dense air on this side, and it drives a wedge underneath, and this air goes up, and when that happens, it creates storm clouds. Okay, so that's how that occurs. So the standard unit of pressure is called a Pascal. More accurately, we measure in kilopascals because atmospheric pressure is like 101,000 kilopascals at sea level. So we usually use that as like the base value. It's kind of like we use kilograms. It's 101,000 kilopascals. But anyhow, sorry, I lost my train of thought there for a moment. Anyhow, pascals are used to measure atmospheric pressure. Okay, again, that's the most commonly used version now. This millimeters of mercury, that was when they first understood pressure, and then atmospheres. Atmospheres are relatively equivalent to kilopascals. One atmosphere is 1.01 times 10 to the third or fifth kilopascals. It's coming up here in a second. Yeah, there it is. Right here. Okay, 1 atmosphere. We won't use this very much, but these two right here and right here are pretty common in chemistry. So standard temperature and pressure, or STP, if you've ever seen that before, is defined as temperature of 0 degrees Celsius, so right at the freezing point of water, at sea level. What is the atmospheric pressure? This. Okay, so you were at sea level and the temperature was freezing, that's what your pressure would be of the atmosphere. As the temperature goes up, obviously the pressure will go up, okay, because the air will expand. Now, these changes are very, very subtle, so it's not a huge difference. You know, from like where we live, which is 800 and some feet above sea level, we're not going to have a much different atmospheric pressure. Now, if you were thousands, plural, of feet above sea level, then you're going to start seeing difference. Okay, and here's an example to convert between atmospheres and millimeters of mercury from kilopascals. Okay, it just walks you through the values using that equality. Again, this is just dimensional analysis, right? So we're going to use conversion factors to do this, right? Based on those equalities you saw above. Okay, and the formatting kind of got off a little bit here, but this is going to get crossed off and down here. Okay, and then this should equal 4.4 atmospheres. Okay, and then this is 3,400 millimeters of mercury. Okay. Okay, sorry for the formatting issues. I didn't see that before it went into Notability. I suppose you guys probably deal with that quite frequently, though. Okay. So now in a vacuum, there'd be an absence of gas, therefore there'd be no pressure. That's why it's 0 millimeters of mercury, or 0 atmospheres. All right, so kinetic energy and temperature. A common misconception about temperature is the fact that it, what is it actually measuring? This is what it's measuring, okay? Right here. It's measuring the movement of the molecules, okay? And you have to use kelvins. If you remember, you take the degree C plus 273, and that equals the value in Kelvin, okay? You're going to make note of that. So as a substance is heated, its particles absorb energy, and as it absorbs more energy, the particles become more excited. They'll move more. In essence, as you transfer heat energy to the particles, their movement will increase. And as their movement increases, their temperature goes up. Conversely, well, just think about a gas. If you're going to warm the gas up, as it gets warmer, it's gaining energy. The molecules will move faster. So, at any given temperature, the particles of all substances, regardless of physical state, have the same average kinetic energy, as long as they have the same temperature. Now, that doesn't mean that they'll all be a solid, liquid, or gas at that temperature, because like room temperature, we have substances that are solids, substances that are liquids, substances that are gases. But they all have the same average kinetic energy, okay? Because the molecules have the same value in terms of their kinetic energy. That's their temperature, right? Now, think about a glass of water sitting on a counter, though. Some of the molecules in there will have more than others, but the temperature of the water would be the average, okay? So if you put a thermometer in there and it said the water is 68 degrees Fahrenheit, or roughly, I think that's like 23 or 27 degrees Celsius, that's the average. Some of them might be over 100 degrees Celsius. Some might be close to zero, but the vast majority are closer to that 68 Fahrenheit or 23 Celsius. Okay. And this is exactly what I was talking about. So here you see the two lines on this chart here for lower temperature and higher temperature water. That purple line represents a warm or hot water, where more of the molecules are towards this side, right? That has higher kinetic energy, okay? The cold water has very few that are on this side of the graph, okay? It drops off sharply, all right? So most of the molecules in the cold water have low amount of kinetic energy, right? That's this graph, right? Right here. And for the warm water, okay, it has many more molecules in this area, right? Let's just cut it off here. The cold water, it had just this little bit down here, okay, which is a very small amount in that warmer range with the higher kinetic energy. Kinetic energy of particles in a substance directly relate to a substance's temperature, as I was describing. If a substance is warm or hot and it's allowed to cool down, basically the molecules are going to lose that energy, okay? I'm sure you've all been in the kitchen when the oven's been on for quite a while. It gets warmer and warmer in there because there are warm molecules being excited because the heating element of the oven, they're escaping, or just the ambient heat coming off the oven is going to warm the room and the molecules in the room, okay? So absolute zero, or negative 273.15 degrees Celsius, is the coldest temperature that can be achieved. This is what's known as absolute zero, okay? In lab settings, scientists have gotten close, but they can't quite get to absolute zero. The only way to get to this probably is to be out in the deepest portions of space where you can hardly even see starlight. That'd be about the only way you could get to that point. The Kelvin temperature of a substance is directly proportional to the average kinetic energy of the particles. So that's what's going to be a part of the formula that you're going to use. And there will be some math that will come with this later. If you have any questions, I'd love for you to express them. I'm planning on having a Zoom meeting later tonight, if it works out well. I'm going to invite all 3 chemistry sections, and I'll put a link in the updates for that if you're interested. All right. Well, that's all. for today. So I hope things are going well for you and you're staying safe and clean and somewhat isolated at home. If you're working, try to keep yourself safe there as well. Have a good night, everybody.